times 4.74 seconds, and that gives us 46.5 meters per second. Of course, the velocity in the x at the end is the same as the velocity in the x at the beginning, which we just solved for on the prior step. So that's 11.2 meters per second, and at this point we can do our triangle. So the y is 46.5 meters per second and the x is 11.2 meters per second. And so then from there, again, it's just Pythagorean. Velocity final is equal to the square root of 11.2 meters per second squared plus 46.45 meters per second squared. And that in the end gives us 47.8 meters per second. And that finishes up that one. Which brings us to our upwardly launched projectile. Here we have a cannon that is being fired, and it's actually being fired at a really shallow angle because this thing goes really far, really fast here. We get 3.68 seconds for our time, and we have 1,200 meters for our distance there. And that may not seem like a lot of initial information to be able to answer all of these questions. Nope, maximum height would be y. But it turns out we can, and we will walk through all of these. So y max equals question mark, velocity in the x equals question marks, velocity in the y. Final speed at firing and impact, this would be velocity initial and velocity final. That's along the path, so that would be combining the x's and y's. And then this is the launch angle. So let's dive right into those. So what is its maximum height? For that, we'll use again our old friend, the distance from free fall equation, which of course is just one of the kinematic equations simplified down because there's no initial values for our velocity or our initial position. Of course, we could be given those and then we could deal with them. So here's where things get interesting with this one, is the time. Because if we want to know the maximum height, if we draw that whole projectile path, that maximum height happens at time 1/2. So we're going to use that here, 3.68 divided by 2 seconds squared. And so then when we punch all that into a calculator, we get 16.6 meters for its maximum height. For horizontal speed, velocity of the x is equal to x final minus x initial over time. It went 1,200 meters. Of course, it started at 0 meters, and the time it took, this would be the full time it took for the flight, would be 3.68 seconds. So then that gives us 326 meters per second. And 3 sig figs on both those. Again, going back to the initial problem, you can see there's 4 sig figs on the distance and 3 on the time, so we're limited to 3 on all of these. Next we have what is its vertical speed. So velocity in the y is equal to y final minus y initial. Well, it started at 0 and ended at 0, but it obviously had some vertical speed. So we're not really looking at that. We're looking at the maximum height it went. And if we're using the maximum height, then we also have to use time 1/2 again. And so a moment ago we calculated that to be 1.84 seconds. You can double check that, 3.68 divided by 2. Again, if you would like to. And again, I'm getting ahead of myself. Should just put that as time in there. And then we'll actually plug in the values here on this step. So 16.6 meters minus 0 meters over the 1/2 time, which is 1.84 seconds. We get 9.03 meters per second. what was its speed at firing and impact. Again, velocity initial is going to be equal to velocity final, so those two have to be the same, so it really doesn't matter which one we solve for, but we now have a velocity in the y direction and a velocity in the x direction, not to scale here. I know even at that exaggerated, it's still not to scale. And so then we're looking at using Pythagorean to figure out the hypotenuse there, and for that we're going to use that velocity final is equal to root. It should be 9.03 meters per second squared plus 326 meters per second squared, and then that gives us a final of 362.2 meters per second, which you will notice when we round off with sig figs, or in other words, the amount of vertical speed that it has is essentially negligible here. And lastly, the moment you've been waiting for, the launch angle, which is trigonometry, of course, and actually using sine, cosines, and tangents. There's actually two ways you can solve this. One is using the distances, and the other is using the velocities. And I'm actually going to work it out both ways, and you'll see we get the same answer either way. So if we're using the distances, we have to remember that the y that we calculated there was the y max. And so if we want to figure out this angle here, we are looking at using half of the x distance. And so half the x distance was 600 meters because the total was 1,200 meters, and the maximum height here was 16.6 meters. And we want to know this launch angle here, the initial launch angle, theta. And so if we want to know that, and of course, this is not to scale, but it looks like we're going to use the tangent function because we know the opposite and adjacent, which I would say tangent is